In the previous video, we have established through a couple of examples that the thermodynamic landscape has 4 independent variables and 4 dependent energy variables. The independent variables are entropy and temperature, pressure and volume. The dependent variables, dependent energy variables, are internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. The reason that we have those 4 different forms of energy reveal themselves in the examples that we have established. Those examples were about finding out how much work is needed under a constraint of, for example, entropy and volume, and we discovered that the shaft work needed under entropy and volume constraints were equal to delta U. Shaft work under the constraints of entropy and pressure was equal to delta H. Shaft work under the constraints of temperature and volume was equal to delta A, or Helmholtz free energy, and shaft work under temperature and pressure constraints was equal to delta G, or Gibbs free energy. Now we are going to start learning a little bit more about those 4 different forms of energies and their interrelationships. It is, for those of you who are mathematically oriented, just consider them the projection of the same energy onto different coordinate systems. Projection of the same energy onto different coordinate systems. So then, again, we also derived the expressions for du as TdS minus PdV for a system which was closed. There was no shaft work done, process was reversible, and so on and so forth. We were looking for the dependency of the internal energy on the independent variables, and this expression and this expression are consistent in a conservative system, that the dependent variable is a function of its independent variables. Now let us write the equivalence of H, A, and G, and from here we will proceed to derive what is called the Maxwell Relations, and Maxwell Relations are going to be very useful for us to navigate through a new realm of the real fluids. The H is equal to TdS plus VdP, and where they come from were derived in the previous video. If you are confused about them, just at the end of the previous video, we derived them one by one. So this is going to be our starting point. dA is equal to minus SdT minus PdV, and dG is equal to minus SdT plus VdP. All right? So internal energy is a function of S and V. Its derivative is this. This expression came from the combination of the first and second law analysis. When we have just applied the relationship between H and U and take the derivative, you obtain this relationship. When we have taken the relationship between Helmholtz free energy and internal energy, we obtained this relationship, and same for G. So let me also remind you that H is equal to U plus PV, A is equal to U minus TS, and G is equal to U plus PV minus TS. Now, we're going to have an excursion in the field of mathematics briefly, and then we will bring back our understanding and apply it to the equations that we see on the board. Now, just let us take an arbitrary function f of xy. Let me just write it here. An arbitrary function f of xy. Its derivative, total derivative, is equal to del f over del x, keeping y constant, times dx, plus del f over del y, keeping x constant, times dy. Say, for example, f of xy is equal to x times y plus y squared over x. Then the derivative should be equal to df. I'm going to keep y constant and take the derivative with respect to x. This is going to be y minus y squared over x squared times dx. I treated y as if it is a constant, as if it were a constant. Now I'm going to do the same. For x, I will maintain x constant and take the derivative with respect to y. And this is going to be x plus 2y over x times dy. Right? This is what I'm talking about. Del f over del x, keeping y constant. Del f over del y, keeping x constant. So, I'm going to take one more step before I go back and apply these rules to the equations that I'm going to derive. Now, if my domain is conservative, if f represents a function that is subject to a conservation law, for example, energy is conserved. Energy is conserved. Then under conservative conditions, the order of differentiation doesn't make any difference. All right? That I can commute the operators in a more complex language. What do I mean? I mean this. So I have taken the derivative of function f with respect to x and kept y constant. And here I have taken the derivative of f with respect to y and kept x constant. Now, if I take a second derivative with respect to the other variable, and here my other variable is y, if I differentiate this function for the other variable, keeping this variable constant, this should be equal to this function taken derivative with respect to the second variable and then later differentiated with respect to the first variable. All right? Keeping y constant. Now let's go ahead and apply this to see if we are going to arrive at the same function. Now this was my x derivative. I kept y constant. Now I'm going to take the y derivative here, right? Let me see. My y derivative here is going to be 1 minus 2y over x squared. All right? And now I'm going to take the x derivative here. All right? Let me see if it is going to come equal. So it is going to be 1 minus 2y over x squared. All right? So now I'm going to apply this to the situations here in terms of thermodynamic variables. And I apply this to derive what we call the Maxwell relationships. I hope that I will be able to do this without erasing anything from the board, because we will refer back to those and will make good use of them. Now, let me compare this one with this one. Now, if my f is u, my df is du, and here du is del u over del s, keeping v constant times ds, plus del u over del v, keeping s constant dv. Now, this and this are analogous. Now, what is my del u over del s at constant v? It is equal to t. What is del u over del v at constant s? Is equal to minus p. Now, I'm going to take them and take their second derivative with respect to the other variable. So I'm going to take the second derivative with respect to the other variable. Here my derivative was with respect to s. Now I'm going to differentiate with respect to v. Del over del v, what was my function? T. What am I going to keep constant? S. Should be equal to del over del s minus p at constant v. Now this is my first Maxwell relationship. Now what does this relationship do? Of course, doing math is fun. Of course, we just enjoy learning new things. But what this Maxwell relationship does is it relates those four different independent variables: temperature, volume, entropy, and pressure. It interrelates how they are related to each other. All right? And those four different forms of energy in the same logic are going to lend us new relationships which we will use to navigate in the thermodynamic landscape. So let me continue here. dH is, let me take this into a frame so that what we are doing is going to be independent from what's written on the screen. Okay. So dH, with the same strategy, I hope that my space will allow me to do, I guess. Now we have del H over del S at constant P times ds, and we're going to have del H over del P at constant S times dP. Okay? Now what is del H over del S at constant P? By analogy, I'm just comparing the coefficients of ds. All right? This is equal to T. I'm comparing the coefficients of dP, and this should be equal to V. Then, corresponding Maxwell relationship. Now I'm going to take this function and take the second derivative with respect to the other independent variable. Del T over del P at constant S is equal to del V over del S at constant P. Now this is my second Maxwell relationship. So let me frame them so that we will be able to differentiate what we are going to use. So now we are going to do the same for Helmholtz free energy and Gibbs free energy. Now dA is equal to del A over del T at constant V dt plus del A over del V at constant T dV. Again, I compare those two equations with one another, and I notice that these are my parameters to be carried to the next stage. So I'm going to take the derivative of minus S with respect to V. I'm going to take the derivative of minus P with respect to T, and they're going to be equal. Del over del V times minus S, keeping T constant, should be equal to del over del T of minus P, keeping V constant, and those minuses cancel one another and they become plus. This is my third set of Maxwell relationship. Let me eliminate those. And let's have the last equation, then we will proceed. So dG is equal to del G over del T at constant P times dt del G over del P at constant T dP. Again, this is equal to minus S, this is equal to V. All right. So I'm going to take minus S, differentiate it with respect to P. I will take V, differentiate with respect to T, and I know that they're going to be equal. Del over del P of minus S, keeping temperature constant, should be equal to del over del T of V, keeping pressure constant. And this is my fourth set of Maxwell relationship. What does a Maxwell relationship do? It identifies the relationship of those four state variables with respect to one another. I will also amend this board with those relationships that we have obtained from the first derivatives, because we are going to be using them also. Del u over del s at constant v is equal to t, and del u over del v at constant s is equal to minus p. Here, del h over del s at constant p is equal to t del h over del p at constant s is equal to v. We have here del a over del t at constant v is equal to minus s, and del a over del v at constant t is equal to minus p. And here we have del g over del t at constant p is equal to minus s, and del g over del p at constant t is equal to v. Now let's see. V is equal to del h over del p at constant s. All right, if I know enthalpy function with respect to pressure, I can take its derivative while keeping entropy constant, and that is going to give me V. I may not have entropy, but I may have Gibbs free energy. Then its first derivative with respect to pressure, keeping T is constant, also gives me V. So if I need V, and I don't have V, and I have G or H, I can obtain volume from those energies. All right? These partial derivatives are our compasses in a way that they are our compass to find the unknown in a thermodynamic landscape. Now we are going to remove the binding condition that internal energy is only a function of temperature. Remember that we were using this relationship for the ideal gases. We said that internal energy of an ideal gas depends only on temperature. And then we derived the relationship between internal energy and the entropy and volume. Now we say that internal energy depends on entropy and volume. But entropy is an independent variable that is a little bit elusive, that we can measure the volume, we can measure the pressure, we can measure the temperature, but entropy is difficult to measure. So as a result, it is convenient to find a domain that we have measurable variables, and we are going to now take this expression and we are going to relate entropy to temperature and volume, and then our internal energy is going to be an accessible function for the measurable variables. Now let's start with this initial form. All right? The fact that we are not able to measure or estimate entropy as easily as temperature, pressure, and volume, we are going to just use the same logic here. We started from internal energy is a function of entropy and volume, or enthalpy is a function of entropy and pressure, and so forth. We move down. All right? Now we are going to take this entropy and we are going to say that let's find the relationship express entropy as a function of temperature and volume, and then substitute here for internal energy as a function of temperature and volume. Now, if entropy is a function of temperature and volume, ds is going to be equal to, with the same mentality, del S over del T at constant V times dt plus del S over del V at constant T dV. Now, del S over del T at constant V is actually related to du. I'm going to take this relationship. Let me do it with a different color, and let's see if we can just get around it without confusing you too much. Or let me just write it. So I will start from du. Again, the same function, TdS minus PdV. I will divide both sides of this equation with dt. Now I have del U over del T, and I will do this at constant volume. Del U over del T, I divided du by dt while keeping volume constant. That's why this is a partial derivative, is going to be equal to T del S over del T at constant V plus minus P del V over del T at constant V. Of course, volume differentiated by keeping volume constant makes it 0, right? And I have obtained a neat relationship between del S over del T and del U over del T at constant V. Remember, remember that du, total derivative of U with respect to T, was equal to CV star for the ideal gas. Now this is the real fluid, a real U. This is going to be C sub V, constant volume heat capacity. This is going to be T del S over del T at constant V, or del S over del T at constant V is equal to, I'm going to take this here, this term is going to be CV over T. I found this one. All right. I managed to replace an entropy function with parameters that I can measure or estimate. Heat capacity is a familiar parameter. Temperature is a measurable parameter. Then I have to convert this del S over del V T I just need to replace the entropy with something like temperature, pressure, volume. Now, when I look at the Maxwell relationships, I just wonder if I can find a temperature pressure equivalent. Hey, I find the equivalent here, that S over del P at constant T is equal to del P over del T at constant V. It was exactly what I was looking for. I'm replacing entropy with pressure, volume, temperature. All right? It's just a matter of convenience. All right. So my ds becomes Cv over T plus del P over del T at constant V times dV. I'm going to take this one, substitute in here to obtain du. Or maybe I should just continue and write du here so that I'm going to have the u relationship. Du is equal to T times ds. T times this function, Cv over T plus del P over del T at constant V times dV. Let me just make this as a square bracket. T ds, this is ds, minus P dV. I will collect the dV terms together to have du as Cv. I have to put a dt here. All right, we forgot to put the dt term here. Cv dt plus T times del P over del T at constant V minus P times dV. This is the most general form of the internal energy it's the most general, important, general. We're going to use from this point on this form of the internal energy to estimate the properties of the real fluids. The next thing I will do, I will derive H. I will remove ds from the dH expression in a similar manner, but this time, instead of temperature and volume, I will express S in terms of temperature and pressure. Why? Because enthalpy has the other variable as pressure. I don't want to introduce a new variable into the domain. I just want to replace entropy with temperature. But remember, we need two state variables to specify the state of a system. And I have to have two state variables to start with. Here I started with temperature and volume. There I will start with temperature and pressure. Now we are going to do the same for the enthalpy. We are going to rescue enthalpy from the entropy dependence, we are going to replace the entropy with its equivalent function of pressure and temperature, and we will extract a similar expression for dH as we did for du. Now, again, I'm going to express entropy as a function of T and P. I will derive ds as del S over del T at constant P dt plus del S over del P at constant T times dP. Again, in order to find this, I will start from dH. TdS plus VdP. I'm going to divide both sides by 1 over dt at constant pressure. So I have del H over del T at constant pressure, that is equal to T del S over del T at constant pressure plus V del P over del T at constant pressure. And of course, pressure is constant. This goes to 0. Del S over del T at constant pressure is 1 over T del H over del T at constant P. And if you remember, dH over dt was equal to Cp star. And here we have del H over del T. Now we are dealing with the real fluids. dH over dt at constant P is Cp. I will bring that T here is equal to del S over del T at constant P. So I have this term, this term. And I have to find something that is going to take me from entropy pressure temperature domain to volume pressure temperature domain. So let's look for it from the Maxwell relationships. Del S over del P, del S over del P at constant T. Del S over del P at constant T, we found, is equal to minus del V over del T at constant P. All right? So ds is equal to del S over del T at constant P dt. This is Cp over T times dt plus del S over del P at constant T. We found it from the Maxwell relationship. Minus del V over del T at constant P times dP. Then I will take this one, substitute in here to find the relationship of H in terms of pressure and temperature. So I will write here, dH is equal to TdS this Cp over T dt minus del V over del T at constant P times dP. And VdP. I will group similar terms together, do a little bit of housekeeping. dH is equal to Cp dt plus square root of square bracket V minus T times del V over del T at constant P times dP. And this is the true form of enthalpy, relating it to all relevant state variables. And here we have started internal energy as a function of entropy and volume. That is the fundamental domain. Internal energy is a function of entropy and volume, but we translated that to a realm of temperature and volume because temperature is a measurable property. Similarly, enthalpy is a function of entropy and pressure. We started from there. That is its fundamental domain. We started from there, and then we moved to a domain where we have an expression that allows us estimate enthalpy in terms of temperature and pressure, because temperature and pressure are measurable. Temperature is a measurable variable, more measurable than entropy. All right, so those two equations are going to take us, are going to allow us to estimate almost all properties of the real fluids. Now, before we say real fluids, we just take our ideal gas, which was P times V to be equal to N times R times T. Maybe I can find a less squeaky pen. Let's try this from this point on. Okay, and let's examine what this is, and let's remove its assumptions one by one. Now, this ideal gas law, as the name implies, is ideal, and it has two major assumptions. One is that volume occupied, this squeaks more. All right. One, volume occupied by the molecules making up the gas is negligible. And two, molecules do not interact. So, in other words, in the ideal gas law, this volume only corresponds to the volume of the gas. The volume of the molecules are so small that we don't even have to take them into consideration. Now, in order to remove this first assumption, what we are going to do is, first of course, we will start from an intensive V, all right? And we are going to account for the volume of the molecules. So if this volume has to be the volume of the void, then I have to subtract from the total volume the volume of the molecules. P is equal to RT over V minus B. And why I converted the equation in this form will be evident in the attempt that I'm going to remove the second assumption. All right? Now, what did I do? This volume is the total volume. I subtract the volume of the molecules, and this expression now allows me to estimate the volume of the void. All right? So this is the first assumption that is removed. The second assumption that I'm going to remove is molecules do not interact. Now, if the molecules interact in the space, now this is one molecule, this is one molecule, few meters apart, all right? Obviously, they don't interact, but as they move closer to closer and closer, right, they will start to feel the force field created by the electron motions around them. And they will be attracted to one another, right? If this is the position, that the pressure brought the molecules together, and if their interaction is attractive, they will move even closer, or in the same volume, they will feel a smaller pressure. All right? In other words, I'm going to have a lower pressure dictated by an intermolecular attractive force constant A, and this attraction requires at least two molecules, and the probability that these molecules will come together is going to be proportional to their concentration. Concentration is 1 over specific volume. So I need two of them. All right? This is attracting this, this is attracting this. So I'm going to have A over V squared. All right? So this is my new expression, new equation of state. This is an equation of state. This is an equation of state. In other words, I determine the state of the fluid by applying any two state variables. And it has a name. It is called by the name of the person who derived this. This is van der Waals equation of state. Okay, van der Waals. From this point on, we will refer to it VDW. For the equation of state, I will use EOS. So it's better to get used to those acronyms we will be using frequently. Now we are going to link the van der Waals equation of state to the internal energy. But before we do that, I will just do a small example of applying the ideal gas equation of state. P is equal to RT over V. And I will find out, I'm curious, I would like to find out what is the relationship, how will this relationship evolve if I substitute P as RT over V. All right? So, what is the U for ideal gas? All right. In order to evaluate the U for ideal gas, I'm going to evaluate del P over del T at constant V. P is equal to RT over V. Del P over del T at constant V is going to be R over V. Then I will write du, which is equal to CV dt plus T del P over del T at constant V, R over V, minus P minus RT over V dV. And you see those terms cancel. And du for ideal gas is CV. Now I take the freedom to put the star dt, and now I have proven that the ideal gas internal energy is only a function of temperature. Right? This is a proof. Now I'm going to do the same analysis for the van der Waals equation of state. Again, I have to find out del P over del T at constant V, del P over del T at constant V for van der Waals equation of state is R over V minus B. V is constant, this term dropped out. And so my internal energy is CV dt plus T times del P over del T at constant V. I will multiply this by T minus P RT over V minus B plus A over V square and of course this has an underscore times dV. All right, just let's make sure that we are consistent. Okay, now these terms cancel one another and my internal energy expression for a van der Waals equation of state is C sub V times dt plus A over V square dV. And now how am I going to calculate the internal energy change? We're going to learn a little bit more about this, but just a sneak preview. If I need to find out internal energy between T2, V2, and T1, V1, I have to integrate this by through a temperature and through a volume integral, but we have to play a strategy. Either we need a real fluid heat capacity C sub V, or we need to take a route that goes through the ideal gas state. That's going to be discussed in the next video.